Hello, everyone. My name is Bobby Jackson, and I'm a postdoc in the Data Informatics and Geophysical Retrievals group at Argonne National Lab. I am going to be presenting today on software I have created for retrieving wind fields from networks of radars as well as multitudes of models. In a way, this software will present a way to synthesize wind data from multiple sources together into one neat little 3D wind field that you can use for analysis. And I call it PyDDA. It's a new Pythonic multiple Doppler analysis package. I'd like to first thank my co-authors on the screen for their valuable input, including Tim Lang and Corey Potvin, especially particular for coming up with the original code that this was translated from, and all the hard work he had put into the original concept of this. I also like to put in as well thanks to the Climate Model Development and Validation activity for funding the production of this software. So I want to just first start from a basic level of view of how do we measure winds in the atmosphere. There are many different ways we do it. And for example, we have a lot of instruments that do point measurements. Like for example, you probably have seen these anemometers on the ground. You've seen various weather stations around the road or even in an open field. So these generally take 2D wind measurements of a point where you get a speed and direction. We also fly through clouds as well, and we can get actually not just 2D, but 3-dimensional wind measurements through clouds that are pretty accurate. But the only issue with these is that these cover very small areas, so without further context, which can be gained from insights from radar images or, for example, reanalyses, without that context, there isn't a whole lot of useful information there. So we need to have further spatial temporal information as well in order to make better use of that data. So going up from there, we go from 2D data points to sort of 1D data points to sort of vertical profiles. We can do through weather balloons, and here's a picture of me getting ready to launch one of these weather balloons. Basically, you have these sensors for relative humidity and winds and temperature attached to a helium balloon, and it rises up through the atmosphere. We also use radar wind profilers. Now these send microwave pulses of radiation up through a vertical column, and what they'll detect the phase shift between the microwave radiation that was set up and back to actually try to detect what the velocity is, and from there you'll get a 2D profile of vertical winds a profile of 2D winds in the atmosphere. Now these are fairly accurate ways to measure, but they only provide sort of straw views to vertical columns. And for example of a measurement here, I'm showing a plot of weather balloon measurements taken in Darwin, Australia during the month of January 2006 as a function of time on the x-axis and pressure on the y-axis. And we can see changes in the large-scale flow, but the issue is this only covers a point. In fact, for a right wind sun, you're not only just covering a point, you're covering a point that could vary 50 kilometers in the x and y direction. So it gives you a little bit of information there. It gives you information about some of the dynamical profile of the atmosphere, but you don't have a lot of 3D statistics. And I'd like to just further plug this plot was made with a new toolkit we developed called Atmospheric Community Toolkit. I will not get more into that in this talk, but you're welcome to talk to me or Scott if you are further interested in that particular package. Also, now finally, we have a large network of radars in the United States. So we have the next generation radars, which we commonly call NextRad, and these provide ample coverage throughout the United States. All the areas in yellow particularly, we get at least coverage at 3,000 feet above ground level. And this encompasses about 90% of the United States. But there are some hard to reach areas, and particularly in the mountains, where we don't have radar coverage. And there are some gaps over here where not a whole lot of people live, so they probably decided it wasn't terribly important to put weather radars there. But we can grab this grabs us a lot more spatial coverage of wind measurements. However, the caveat here is that these radars, they don't measure the 2-dimensional wind. What they actually measure are the velocity of scatterers going in the direction of the radar beam. So all you get here, for example, on the left here, we have an example radio velocity image from the SciPy radar, one of these types of scanning radars. And on the right, we have another one of these from another radar down, and these are both in Darwin, Australia. So I show these as example, but the NextRad radars are the same type of radar. So this is applicable to that network as well. But we only get, for example, we only know if we're having echoes that are or if our particles are moving 20 meters a second away from the radar, or 20 meters a second towards the radar, or some range in between, or just some sort of value like that. So we don't have full 3D information. We only have one component. So we need to have a network of radars as well as information from other sensors and models to create a full 3D picture of the wind field. And how have we typically done this? Well, one common technique is called the 3D variational technique. Now what this does, it minimizes a cost function J that is essentially a component of smaller cost functions that look at the error between, basically do we find the wind field that minimizes the error between the radial velocity and the retrieve winds, or whether or not we're following mass conservation, or whether how smooth the wind field is, or just deviation from other laws of physics. And we could take one of these and prescribe a constant to tell us how important is that to our retrieval. So that's what these C constants here in this equation regard. And that is what we're basing PyDDA, this retrieval package, off of. Now there are some existing toolkits out there for these type of wind retrievals. One is called CDRIC, custom editing and display of reduced information in Cartesian space. This one uses a slightly different technique that actually does a strong, it actually integrates the mass continuity equation in the vertical in order to try to get U, V, and W. And then it uses other utilities for regrid and gridding, and then there are confusing scripts that I will show in a second that can be used as inputs for CDRIC. There's also multi-dop. Now this one is a Python wrapper around a C package called DDA, and it is basically, it does have some dependence on open source packages in the ecosystem, including the Python ARM Radar toolkit, which is a commonly used open source package that is used to develop, maybe is used to analyze and visualize radar data. But there are some flaws with it. It doesn't scale it's not thread safe. It doesn't run, you can't run it on a Windows machine if somebody happens to have that. And DDA itself has to be compiled from old C and Fortran code. And it's based on rather legacy code. And if you try to put the input dictionary, it is still rather cumbersome. But if you're interested in looking at that, that is available at github.com/nasa/multidop. And I'll just show an example of how hard CDRIC is to use by just showing one example script of how you input it. And I'm going to tell you immediately, I don't want to bother with this. It's like, what is patcher vedit decilock 3.0? Nobody cares. I don't want to do this. So this is what, that alone would motivate me to develop my own Python package called PyDDA. And it's again built off the Python ARM Radar toolkit. So many in the room some in the room have probably used this at some point, but it's a commonly used utility for radar analysis. Again, based off the 3D variational technique, and you can support as many radars as you need. You can customize initialization fields, and I'll go into that more in a second. And you can also integrate in model data. And I currently have support for WRF, HER, and ERA interim. Runs on Windows, and you can do a pip install or a conda install. So it's easy. It's already available on CondaForge, so you can just install it from CondaForge today if you want to give it a try. Now, what I'm going to go into next here, I'm going to just open up a notebook of a live demo I have of just some of the features of PyDDA. So first, all you got to do, import PyDDA. So when you do your imports, it's just a bit in PyArt just to load the data, and PyDDA to go in and load the analysis package. So first, I have a couple of example grids that I load, and that's just done using PyArt's I/O module. And then particularly, the next thing we have to do, it needs an initial guess for the wind field. The optimization loop, or the loop requires an initial guess at the wind field before it can start doing the retrieval. So I'm going to go ahead and put in a sounding that I have stored in here, and we can use PyArt's capability for reading sounding data and then put that in as an initialization. Now, finally, we can just retrieve the wind field with one line of code. The minimum you need to put are the list of grids and the initialization field. And then optional parameters here could help you refine your retrieval further by adjusting the constants or telling PyDDA what the names of your velocity variables are. And into some of these fields like vel name equals VT. But in the end, it's just down to one line of code to retrieve the grids. Now I'm going to start doing a multiple Doppler retrieval here. And one of the nice things about it is that I'm going to be able to finish it here in the length of this talk, because most of the other codes out there will take at least 5 to 10 minutes minimum to retrieve a wind field here. But this will be done here in about 60 seconds. And that just shows how easily usable this retrieval software is. But while this is going, I'm going to go ahead and at least start preparing you for some of the other features that PyDDA has. So you can make once you're done, you can make quick look plots of the data, including bar plots, so you can select what level you want, and then you can preview your wind field that you're going to have over say reflectivity. So if you want to view the winds and reflectivity together, you can put over the wind field, and there's even support for putting contours on top so that you know more where you can get some more detail on where your exact winds are. So we still got 10, so that this runs about 40 iterations. We could also do horizontal cross sections of wind barbs as well, and there's another horizontal cross section here. But we don't just do wind barbs. We're going to go ahead, we also do streamline plots here. And from an example we can see here, we can see here, we have generally winds from the northwest blowing to the southeast, except when you get to your most intense echoes here, you can see here I specify the vertical velocity contours, and you can actually see the updrafts that fuel these storms that are coming through. So it is able to resolve all of those important features of the storm. Now it is done. So it got done in about 70 seconds. So I was able to do a multi-Doppler wind retrieval while talking to you here. And then now I can visualize it with these 2 lines of code, with easily adjustable options like adjusting the space of the barbs. So let's say I want the barbs and the Y a little bit closer together. Now you've got some more barbs. And similar features here and here. But in any case, this just shows you how easy you could get from retrieval to quick visualization in just a matter of a couple minutes using this software. Now I'm going to go back, and I'm going to go in and go into some more details about what the capabilities of PyDDA. And I will end the talk with several neat examples to look at, including some cool animations in a hurricane and a tornado. So I will start here. So the way PyDDA works, as I mentioned earlier, you have a cost function and initial guess, and you have to go ahead and basically what's done is I find a minimum here in this curve here, as you can see, right there. Now, the most rudimentary way to do this, it's not the most sophisticated way to do this. This one is just called a simple steepest gradient descent method. And what you'll do here is that you'll step down a constant factor of the gradient as you go down until you reach this minimum here. And once the gradient is relatively flat, which we usually say, hey, the norm of the gradient is less than 1.01 or 0.01 or something like that, then we know we've reached convergence. Now we get from SciPy uses a different variant of this that allows for physical box constraints and faster convergence so that it knows that the solution is going to be physically realistic and be able to take advantage of those constraints to speed up the retrieval. It's also, I want to get into the fact that your initialization might matter. For example, if you start over here on this end of the curve, you'll be down here. The reverse back direction of the gradient gets you down here, not down here. So you could have a completely different wind field and not even intend that you would have it. So that's why we have an initialization module where we can go ahead and specify the differing initializations that we can feed into the module. So we have a module that gets you a constant wind field, one from a sounding, one from WRF, and one from the HER. And there's room to add, and I believe I also have one for ERA interim too. So there's a room to add a custom initialization for your module. And currently we support WRF, HER, and ERA interim. So creating custom constraints, we also can create a constraint against a model that actually goes into the cost function itself. So at every step, you're creating a soft constraint against a particular model field. And what you can do here, I have an example for ERA interim, WRF, wind field, and also we can do from sounding and from constant wind field. And there is even support for the automatic download. If you have an ECMWF account, you can automatically download area interim data, and then it will automatically interpolate it to your radar's coordinates. So it can do all that dirty work for you, and then all you have to do is just do the retrieval. We also have a module for cost functions here. So each cost function is in its own routine that if you go through the documentation and go through the code, it is easily accessible. You can easily look for it in the code so that if somebody wants to make a change, they're not going to be sifting through a bunch of different confusing routines. Unlike in, for example, I think in the DDA code, it was fairly difficult to find all the functions, but now it's all organized in a neat little way. So now that I've gone through some more of the technical details behind PyDDA, I'm going to get in the next part of the talk, just show some cool examples of data that we can do with that we can retrieve from this. So here's one example here where I am looking at data from the HER and two NextRad radars. In particular, the locations are given here, in particular out in North Carolina. And what we could do here is actually retrieve the winds in hurricane. This is a retrieval in Hurricane Florence, when it was within the range of these two radars. And what we see over here, one, we are definitely getting the winds moving to the west as we go, but we're also particularly able to capture some of these finer scale details here. What these contours represent, the red represents the contours of hurricane force winds, and the blue represents gale force winds. So here it basically tells us where the damaging winds are currently occurring in the storm. What we just overlaid upon is the rainfall rate currently estimated through an empirical relationship. And what we can see here, corresponding to some of these heavier rains, we can actually see what almost looks to be different downbursts here, where there are accelerations in the wind that are associated with these outer rain bands. So you can see details in here that you may not normally have been able to see by just looking at a forecast, but you could actually see little higher gusts that could be occurring. And I could expand this out. There's even support for that. If you can just put in a dask cluster, you can actually distribute your work out to multiple machines. And what I've done with this is I have done a retrieval with 6 radars, HER and the area interim, and put it all on the screen. And what you can see over here is that we're able to retrieve a hurricane and this spans 1,200 kilometers by 1,200 kilometers. And this run was done on 6 36 core machines at about 20 minutes. So you do need some computing power to get this done. But if you have a cluster, you can definitely retrieve winds over very large regions that you were not unable to do with past software. Also, the next example, I want to show a tornado that went through Sydney, Australia. So here we have a network of 4 radars here, and these 4 circles represent the maximum range of each radar. Basically, if it goes past that, we can't rely upon any data past that point. And all these have a maximum range of about 200 kilometers or so. So basically, during this day is that we had a tornado go over Sydney, right over here, as we can see over here. Now I will go in and do a further zooming in of this figure, and what I see, in particular, we see the clockwise rotation. Now remember, we're down under, so tornadoes spin clockwise in the southern hemisphere, but we can see the clockwise rotation here associated with the supercell, in particular in the mesocyclone here. And if you're looking at the winds, we're looking at about 40 meters per second winds. So it's likely that there's at least if those winds are mixed into the surface, there could be an EF1 there present in that scan. I'd like to do a final example of a cool retrieval we've done. So we have 2 X-zappers, the Vance Radar in Oklahoma, and the HER in north central Oklahoma. So the ARM program has 2 radars that we're scanning simultaneously for one particular weak thunderstorm event, the 2 X-band radars. Now these have differing, because they're at X-band, they have differing detection ways, different ranges of where they can detect winds, compared to the Vance radar at S-band, which has a wider range of winds it can detect. Now, radars can only detect a certain range of winds because they are limited by the amount of pulses you put out, and then between the one pulse and the next pulse, if you have a phase difference in the waves that wraps above one period, you might actually have what's called aliasing, and that limits to how much the speed of the winds you can detect back before doing corrections. But anyways, the fact that we can integrate all these differing data sources together and put them in this plot. Now we got over here, we have the wind barbs here plotting as the storm moves up to the north-northeast. And then what we have, if we can see basically essentially a frontal passage through, we get southerly winds shifting to southwesterly winds, indicating the passage of a cold front as this storm rolls through. Now I want to finally just link everybody to the website here. And I can go and put that in. But if you want to go on the website and look at all the different examples of documentation, it's just openradarscience.org/PyDDA. And this shows you how to install it. So you can do pip install or conda install. And as well, there's a different contributors guide if you wish to contribute with all the different guidelines that we have. An example gallery if you want to get yourself started. So there's 6 examples that you can run on the website if you want to teach yourself how to use it, as well as a reference manual for what each one of these does. Each one of these functions does. So all the functions that are in it are documented, and you know what each one will do. And we'd like to wrap up the talk here. As you look at, this package is already being used by government institutions, and particularly NASA has taken an interest in using PyDDA for validation of the ACCP, or aerosols and convection precipitation decadal survey mission. And what they're using PyDDA to do, they're retrieving winds from 2 radars, one NOAA radar, one NASA radar, and they're using these to validate spaceborne retrievals of winds. So they want to basically they're going to use this software to produce ground observations that go ahead and produce the validation that is required in order to gauge how well the spaceborne retrievals are doing. And we can see over here that it definitely has been working for the set of validation radars that they have been using. You can see the details of storms with the differing updrafts, as well as you can see this rising updraft and then the downdraft coming in on that leading edge of the storm. So we can see that it is definitely working for them. So in summary, I developed a new retrieval package developed in Python that retrieves winds from networks of radars with support for assimilation of model and Ray-Winson data. And it can create quick look plots, and it's an expandable framework. And we're looking for people to contribute to this project. So part of the roadmap, we're interested in getting point observations. We're interested in supporting a larger number of models. We're interested in fixing up the documentation, maybe making the documentation more accessible to non-English speakers, including differing versions in different languages, and other such contributions would be welcome. So at this point, I will go ahead and take questions from the audience. If you want to go and install it today, it's as easy as either one of these 2 commands. If you have conda, you can just do conda install or pip install, or you go to this website and download it. And I'd like to thank you very much for attending, and if you have any questions, now's the time.
Thanks, Bobby. That was a really interesting talk. Yeah. It seems to be what I'm hearing today is that a lot of people like yourself are rewriting legacy code. So do you think that there's some future where earth science graduate students don't have to learn Fortran anymore?
I'm thinking that, I'm hoping, that's what I hope for the future. Because if we don't have to, probably we're stuck in Fortran. So while that's still in Fortran, I think Fortran will stick around. But if they could get that, even if they got that to C++ or something, that would be great. So I'm not sure about Python may not be fast enough, but we'll see.
Very cool. So any questions for Bobby? Yeah.
I'm curious as to how well your final wind retrievals, is that me somehow? The cell phone? How well your wind retrievals compare to HRR itself, which is obviously assimilating radar data, right, to begin with.
What I've done with my final, particularly as far as how well they compare to the original ones, I've actually done a comparison between what what I've done is I've done a retrieval with just HRR, no radar, and then you do it with the radar data. And there's definitely a few meters per second shift where we have the radar data, usually within 1 or 2 meters per second. So we can tell that it's not just integrating in the HRR data, but we're getting in finer details that would not normally be in there. HRR is at 3.7 kilometer resolution, and this data is at 500 meter resolution. So that's probably a lot of it, is that we're just getting a lot of that finer scale detail. So no, that's something I've definitely checked. Yep.
Your roadmap says support for point analysis such as wind profilers. How would PyDDA help that?
I think in particular, what I envision in putting in there is that potentially maybe like an extra cost function in there. What that would do is you can weight particular wind observations against one where the wind profiler is, and then maybe say put it back if you're using it for square law to weight that constraint based on how far you are from the wind profiler. That's basically what I envision putting in there. And then you can just have that one vertical profile, and then as you get further away from it, as R squared, it weighs it less and less.
Excellent.
Bobby? No? All right. Well, thanks a lot, Bobby.